Hey guys, it's Charlie, and welcome to another lecture in our TJML virtual lecture series. So, just like last time, I'll be giving this lecture in this Khan Academy-esque style. And like always, if you have any questions, any comments, feel free to let me know down below in the comments on Facebook, YouTube, or you can DM me. But yeah, without any further ado, let's get started. So today, we are going to be covering a brief introduction into the concept of reinforcement learning. Before we get started, as a bit of background, so we've talked about two of the main three categories of machine learning so far this year: supervised learning, unsupervised learning, and we have yet to touch on to reinforcement learning. So how would I describe reinforcement learning? I would describe it as basically learning through experience, having various trials, successes, failures, and using this experience to create this kind of very ideal strategy that you can use to work through a problem. The two key points I want you guys to keep in mind as we talk about reinforcement learning are the concept of experience and learning from past experience, as these are basically the core tenets of any reinforcement learning system, being able to build on past experience to improve a strategy to solve future problems. Okay, so before we dive any deeper, we need to define a few key terms first. The first term we're going to define is an agent. So what would you consider an agent? Well, the agent is basically a trained actor for the reinforcement learning system, for it to basically take in the information from around it, from its state, and use this information and act on it and carry out a specific action. So you can basically think of the agent as being the entity responsible for reading the state and then carrying out an action based on the state. So the next term we're going to have to define is something called an episode. An episode, you can view it as basically a sequential series of states, actions, and rewards that starts with some kind of initial state and ends in a terminal state. So for a brief example, let's say you are playing a game. An episode would consist of you starting the game, doing everything needed to complete the game or alternatively fail at the game, and then the game ending. And one run of that entire process through the game would be considered an episode. And we'll delve into this a bit more later. So the next term we're going to have to define is a state. Like I said before, an episode consists of states, actions, and rewards. But what does that mean? So a state can be viewed as basically any variant of the environment at any given time. If we go back to our game example, a state could be your initial state, so how the game starts out, or it could be what the environment around you looks like after your character in the game takes a specific action. And any action that you take will change the state of your environment. And this brings us to defining the term called action. So like the name implies, so at any given state, the agent can take an action that will basically transform a state S into a state S prime. And moving on, there's also a concept called a reward. And a reward is also exactly what it sounds like. It's a positive or negative value that is given to the agent after it completes an action that takes it into a new state. And this reward can either be beneficial or detrimental to the agent, but it's basically feedback for the agent for it to know if the action it took at a state was a good action or a not so good action. And we can see all this labeled. And going back to the concept of an episode, the episode is a continuous process of being in a state, having your agent act on that state and take some kind of action, and getting a reward for that action, whether it be a good reward or a bad reward, and now you're in a new state. And from this new state, you repeat the process over. You take another action, get another reward, and keep on going until either infinity or until you reach a terminal state and your episode ends. And in most reinforcement learning systems where you're training a reinforcement learning model, you're going to have to go through many, many, many episodes for your RL model to be able to become decent at what you want it to do. And this makes sense because once again, we just go back to the concept of experience, right? If you're playing a game, you want to play that game as many times as possible to get the maximum amount of experience as possible. And you learn from everything you do in each episode. And eventually, after playing enough episodes, after getting enough experience, you're going to slowly start improving. And this is pretty much analogous to the way that RL systems work and how they're trained. Okay, so moving on, we need to highlight a few key things that we're going to be dealing with in this lecture. So in all the systems we're going to be mentioning in this lecture, we're only going to be working with discrete action spaces. So what this means is that our actions, all of the actions that we can take at any given state, they're only going to be discrete out of a selected set. This means that we're not going to have to ever take an action like setting, let's say, a rod to go a specific velocity, either left or right. Instead, we're only going to be telling the rod to go left or right as two separate actions that we can take. This will simplify the actions we have to take, because with this discrete action space, we can compare how good each action is compared to each other action in the action space. The next thing that we have to take into account is that we're going to have total visibility in all the systems that we train. And all this means is that the entire environment as part of the state is going to be visible for the agent at any given point. So at no state is there ever going to be an obstruction of visibility, or is there ever going to be information that could be used in the decision-making process by the agent that will be obscured. That's never going to happen. We're doing this once again for simplicity's sake, but in the real world, this may not always be the case, and the agent may not always have all of the information that it could have at the time of decision making. So with all of this said, let us dive into an example. So this is a pretty well-known game called Flappy Bird, and I feel like it's a very good example that can be used to showcase some of the basic concepts of reinforcement learning. So as you all know, in Flappy Bird, you have different kinds of tunnels, I'll call them walls, and each of these walls has a gap located in a different height. And the goal of the game is to get the bird through as many of these gaps as possible. And you can take two actions. So your action space is essentially just these two actions, which are flapping the bird up so that the bird moves up into a higher Y value, or letting the bird fall to a lower Y value. And most of the time, your action space is not going to be limited. The only times where your action space will be limited are if the bird is already at the ceiling of the game and you won't have the option to go up and your only action you can take is going down, or you're at the floor. But in most cases, you will be able to choose to go up or down. And you have total visibility here again. So the agent that is controlling the bird will always know what obstacles are ahead of it and where the obstacles are. So to define some basic rewards in this game, Flappy Bird is actually an infinite game. So you're not ever going to reach a terminal state if you play perfectly, if you play with an ideal strategy, but you are going to reach a terminal state if the bird collides with one of the walls, ending the game and ending the episode. So let's just define an arbitrary reward for going through one of the walls or passing through one of the gaps successfully. And we can call that as a +1 reward. So every single time you go through or the bird goes through a gap, it gets a reward of +1. And every time it hits a wall, so every time it hits a wall and it goes into that terminal state ending the episode, we're going to give it a final reward of -5. Basically, as this really big consequence, this very big punishment towards the reinforcement learning model that's being trained, showing it, hey, you can't collide into walls as this will end your game and this is very, very bad. But otherwise, if it goes through all of these 4 walls perfectly, it'll be able to get a total reward of +4 for +1 for each of the walls. And the goal is to have the reinforcement learning model slowly over time learn how to control the actions the bird takes, learn how to control these actions to manipulate the bird's Y position, and learn a near-ideal strategy to get through the gaps, thereby trying to maximize the possible reward that it can get. And we as humans who know how to play this game know that the ideal strategy is to go up or down so that the y-axis, the y height of the bird, is the same as the y height of the next gap. But the reinforcement learning model, the agent, doesn't know any of this. So it has to learn from scratch and be able to learn this ideal strategy on its own without any of the basic intuition that we possess. So now we have to touch on some of the background concepts that really lie behind reinforcement learning. The first thing we're going to talk about is a Markov decision process, or a process having the Markov property. So what does being an MDP mean? Well, for any system to be an MDP, simply it has to be both independent, make independent decisions, and also be quote-unquote memoryless. So what this really means is that any future decisions are not going to be based off of any past actions taken or past rewards received, but only based on the current state that the agent is at. So to give an example, if you start off at state S0 and you're currently at state Si, and one way you got from S0 to Si was through a whole slew of different states of actions and different rewards, and another way you can get from S0 to Si is just by taking one intermediate state and two actions and two rewards. Once you reach that point Si, your next action is not at all going to be influenced by your previous actions, your previous states, or your previous rewards. Therefore, the decision that the agent makes at state Si is independent. It's independent decision making. And no matter what experiences the agent had before reaching this state, the action chosen will be independent of all of that. So the reinforcement learning systems we're going to be looking at, they all can be expressed as Markov decision processes. So whenever we're at a certain state, we don't have to worry about what previous states that we took to get there. We only have to evaluate our future decisions based on what we know in the present. Another small example might be from economics, actually, and the concept of sunk costs. If you already sunk a cost into something, your future decision should be based only on what you experience in the present, and not based on any of your previous decisions, as what yields you the best result is going to be determined only on what you're experiencing right now. So next, we're going to have to define a policy for our reinforcement learning agent. So the policy is usually expressed as pi, and the policy is basically a distribution of the probabilities of the actions that we could take at any given state. So let's say, for example, you're at state Si, and you have three actions in your action space, and you want to see which of these actions you should take. So your policy function is going to take in pi of Si and Ai, or A1, A2, A3, and your policy is basically this function that yields you a probability distribution for each action. And once again, this all goes back to the concept of an action space. And your action space ultimately determines what actions you're going to take, as it restricts the actions that are open for you to take. And another topic that we're going to have to discuss is the concept of exploration versus exploitation. So at any given time, an RL agent can choose to either explore or exploit. And if it tries to exploit, then it will follow the policy pi and choose an action dictated by its policy. This will commonly be the action it believes to be the most correct. On the other hand, if it chooses to explore, then it will take an unusual action, so an action not dictated by the policy. And ways it could do this are either just choosing a random action from a set of discrete actions, or it could add some kind of noise to the action defined by the policy. The reason that we have to have our agent explore sometimes, especially if the agent is untrained or inexperienced, is because the policy that the agent thinks to be the best policy may not actually be the best policy. Because remember, we're always searching for the best policy, not just any good policy. So we want to sometimes, I guess, leap out of our comfort zone and be able to take a random action to explore a different trajectory of actions or a different avenue to see if this random action is going to create a new opportunity for us that may actually lead to us learning a policy that is more ideal than our previously thought ideal policy. That's why the concept of exploration is key to gaining more experience, right? The more possibilities that you're able to explore, the more likely it is that you're going to find your ideal policy eventually. So the action of always following your policy pi, always exploiting, is called basically following a greedy policy. And we can add something called an epsilon value between 0 and 1 that will basically create something called an epsilon greedy policy. And what this does is that it creates a balance between exploration and exploitation. So let's say that our epsilon is set at 0.95 per se. This means that 95% of the time, at 95% of the states that the agent reaches, the agent will exploit and follow its current policy. But also at 1 minus 0.95 or 5% of the time, it's going to alternatively take the decision to explore, maybe choose a random action, and see if that random action actually leads to it learning a better policy. This way, it creates this really nice balance between doing what you think is right or what you've previously experienced is right, and also being open to trying new things and seeing if what you choose to do will lead you to learning something that is better. So, moving on, the next thing we have to talk about is a value function. So, a value function really goes back to the concept of finding the best action to take in any given state. And remember, since we're working with this action space that's discrete, we want to choose the single action out of our set of actions that we can take that will yield us the maximum expected future reward. And each of these words is really important into defining the concept of what our value function actually does. So maximum is pretty self-explanatory. You want to maximize something. Reward also is pretty self-explanatory. You're getting a reward at each state and you want to maximize these rewards. The key part here is the future expected rewards. So basically we want our value function, when it's evaluating states on how good a state is quantitatively, we want it not only to care about the immediate rewards, the immediate benefits taking a specific action at the state will yield, but also about all of the other benefits that could be received if you take a specific action. And essentially it's just a problem of comparing a long-run benefit versus some short-run immediate gain. And when we say a trajectory in the long run, we're assuming that the agent is going to continue following the same policy pi. So since the policy will be consistent, that means that taking some action might eventually lead you to more lucrative actions, or lucrative rewards, sorry, but some other actions might lead you to a lot of reward in the short run, but will open you to less lucrative rewards in the future. And we've always got to keep the overall goal of this RL agent in mind, which is to allow us to gain the maximum rewards total. So out of the total time of the episode that the agent is running. So we don't only care about the present, but we care about the long run. And another way we could view this is as a cumulative reward over our current state and all of our future expected states following the actions that we decide to take. And one last thing to keep in mind is that since we can define our problem as being Markov or having the Markov decision property, our value function only needs to evaluate the current state we're in to determine this total expected future rewards, as once again, the future isn't influenced by the past, but only by your current state. So one of the last topics that we're going to have to explain is the concept of how we want to discount a cumulative reward and the Bellman equation. So we have to define what a discount factor is. And basically we can view this as kind of a trust level for our future and our future predictions. So to put this in real world terms, it's easy to predict where you might be or what you might do a few seconds from now or even a minute from now, but it's probably going to be harder to predict where you're going to be an hour from now and nearly impossible for you to predict where you're going to be a day from now. So it's about this concept of knowing how well you can predict the future at any certain time point in the future. This is important because if we remember back to our value function, we're trying to maximize our total future rewards. But also, we have to start trusting the future less and less. Or our predictions of the future, I might say, less and less, as we look further and further into the future. And this is why this discount factor is important. So our discount factor can be defined as a number from 0 to 1, and it plays into the Bellman equation. So below here, I'm writing the Bellman equation, which tries to define this concept of a total cumulative future reward. So we can see here that we're trying to define the value of the current state, or our value function. And we're going to define this as R of Si and Ai, which are the current state and the current action. And this entire R function yields the immediate reward. So the reward that we get at Si after we execute the action Ai. The latter part of this equation has our discount factor gamma, and we multiply this discount factor by a recursive mention of our value function. So v, the value of s at I plus 1 and a at I plus 1. So basically this equation acts recursively in the sense such that we're predicting the current value function of our current state based on the immediate reward that we know that we can discern instantly after taking the action, and adding on the value function for the next state. And if you think about this as this kind of recursive function, this recursive problem, we can see that for every step in the future, our gamma, our discount factor, is going to be multiplied exponentially. So the value of state I plus 2 and action I plus 2 is going to be discounted by gamma squared, and for the next step, gamma cubed, etc., etc. So this shows how we're slowly trusting our future predictions for the value less and less as we go further and further into the future. One last pretty cool topic that I want to touch on is the concept of encouraging rewards, or different kinds of reward functions or agent rewards that we can apply to our agent in our environment. So, as previously said, the reward is something that is defined by the environment, and you are rewarded every time you go from any state to a subsequent state after taking some action at your current state. Now, the rewards that we are working with in our example of the Flappy Bird problem were positive rewards during every passing of a wall, and a very negative reward every time you failed or you hit a wall. But there were no intermediate rewards. So in the states, in the time steps, that the bird was flapping around in the air between when it started and when it reached a wall, or between two walls, the agent wasn't really getting any reward from the environment. This is fine because eventually the agent will explore enough and eventually make a correct action that will lead it to learning how to get the small incremental rewards from passing the walls, but there's no feedback in between those times. So one way that we could essentially speed up our learning process a bit is by creating these kinds of incremental encouragement rewards in between states. So instead of only rewarding the agent after it completes a goal, such as passing through the wall, we can always reward it in between states for doing actions that seem to be leading it into a better position to solve the challenge. A way to do this in this example is having these three birds. So these three different scenarios where the bird is very high above the gap, a little bit almost at the gap, and kind of low compared to the gap. And we as people who know how to win this game intuitively know that if the bird is able to match its y value to the y value of the gap, then the bird will be able to cross through the gap. So we can apply this kind of incremental small reward to the bird every time it makes an action that results in its y value going closer to the gap. So let's say in two intermediate states, the blue bird decides to go up or make the action of flying upwards. Then that will put the blue bird at a y value closer to the y value of the gap. So we can reward the blue bird based on this y value. Now for the bird in the middle, it's already really, really close to the gap. So this is really good for this bird, and we don't want this bird to change. So at any state where the bird is close to this y value, we can give it a larger incremental reward for every state that it is in a near position to the gap. So the bird will be encouraged to stay close to the gap. And with this kind of encouragement reward, we're able to train the agent to recognize when it's taking actions that are beneficial, albeit slightly, to its total final reward, and when it's taking actions that's not. And this doesn't mean that we don't have rewards at the states where the bird succeeds and crosses the wall. No, these rewards are still there, and they're much bigger in magnitude than the small incremental rewards the birds get. So the bird is always still encouraged to complete its final goal. It just gets, say, a little nudge on its way there. And like I said before, some of the benefits that can arise from encouraging the agent to go in the right direction based on these rewards is that faster training might be yielded from this process. Some downsides or some cons to this are that it only really works if there is some kind of simple, intuitive, and known solution. Like in this game, Flappy Bird, where us humans are able to manipulate this reward function for the reinforcement learning agent to basically get a boost in learning. But it may not be ideal for some tasks, such as, let's say, a maze, right? If we try to use this linear distance metric for a maze, then the agent might try to travel directly to the end of the maze, but there might be a dead end there, which won't prove beneficial for the agent. So a linear distance metric in situations like these will not be ideal. So finally, to wrap this all up, we can talk about how neural networks actually fit in with this. So for our reinforcement learning agent to train, we can take advantage of the power of neural networks. And for a complex environment, right, our agent is not nearly going to be able to explore every single possible state and memorize the best action to take at each one of these states. It's way too memory inefficient, and you're definitely not going to have the computational power or the time to brute force a solution to a problem with a large state space or a large action space. Instead, we can leverage the power of neural networks to basically approximate our value function instead of rigorously finding it through trial and error. So one of the most common reinforcement learning neural networks is called a deep Q network, or a DQN. So the purpose of a DQN is to basically estimate a value function, and it's trained in a similar fashion to basically any neural network. And as you can see in this very simple example, there's a fully connected neural network with two intermediate layers, and the output is basically a value function that evaluates a state and an action that we decide to take. And our inputs can be different parts of our state. So, such as the Y position of the bird, maybe, the Y position of the pass through the wall, the X distance from the bird to the wall, and etc., etc. The purpose of the DQN is basically to learn the most ideal value function that it can learn. And from using this value function, we can basically have a simple policy where we take the state and take an action, the two actions we could take, up or down, and then evaluate both of them to see which is the better action by our policy and by our value function. And remember, we can determine what our most ideal action is through seeing what action given that state will yield the maximum future expected reward in accordance with the value function. And just as a brief overview, many of these reinforcement learning systems, or I guess all of them, require many, many episodes of training in order to develop a good approximation of a value function and thereby a well-functioning agent. And this means that a lot of reinforcement learning training is usually very time-intensive for any tasks that are not trivial. But we always got to keep in mind the concept of experience. And usually the more episodes you can get, the better. Because the more experience you can have, the more optimal your value function that you're training through your DQN is going to be. And just for a brief takeaway, we can do an overview of this entire process. So through every episode, like previously mentioned, we start off with an initial state and we eventually come to a terminal state. And in between this initial state and this terminal state, we go through a series of states, actions, and rewards. So from your initial state, you're going to take some action that yields some reward once you get to some subsequent state, S1. And you repeat this process, you keep on going. And your agent is in charge of making these actions and trying to get you the maximum possible future reward. And if the agent can maximize, in this case, the sum of R1, R2, and R3 to be the best it can be, then the agent has succeeded. And yeah, just this state action reward process is very essential and very key to reinforcement learning. So just as a brief conclusion, all of these topics explained today are just a brief intro to this wide field of study of reinforcement learning. And with much experience, with much training, reinforcement learning systems are able to best humans at very non-trivial tasks, which is really, really impressive. And reinforcement learning is going to power the next generation of artificial intelligence, and there's many practical feature applications. Anything from like managing network, server infrastructure, self-driving cars, anything that a human can learn to do, a reinforcement learning system now or in the future will probably be able to do it. So thank you guys so much for listening, and thank you so much for watching this lecture. As always, if you have any questions or anything else, just drop a comment down in the comment sections below and I will get back to you. Thank you so much for tuning in, and I hope to see you again next time.